This is a brief introduction to electric circuits where we will look at some of the key ideas. This is a wire, so it's a zoom in on the wire. And if we looked very closely in that wire, we would find that there were a lot of electrons in the wire that aren't really firmly attached to the atoms. This is a property of metals, that they have these free electrons. Now these electrons aren't moving anywhere in particular at the moment. They are probably just jiggling around a bit. If we applied an electric field throughout this wire by putting a negative at the top and a positive at the bottom, then each of those electrons feels a net force in one direction, which is towards the positive end and away from the negative end. Now this is a bit like a gravitational field. Any mass in a gravitational field will feel a force just like the charged particles feel a force in the electric field. Just like we've seen before when we talked about energy, a mass that is higher up in the field has a higher gravitational potential energy. And in the same way, an electron that is far away from the positive end of that wire will actually have a higher electrical potential energy. And the same when we look at low heights, we have low potential energy, and when that electron is near the positive end, it has a low electric potential energy. What we're going to do now is look what happens when we take this end of the wire here and bump it up against this end of the wire. And I'm going to redraw that here. So here's my negative and here's my positive, and the wire is going to go all the way around in what we call a circuit. Now the symbol for that positive end of the wire is a long bar, and for a small bar, and this represents what we call a cell, so a battery or some kind of power supply. Now, even though we have bent this wire around, the electric field is still pushing the electrons away from that negative end and towards the positive end. Now, just for interest, this positive end is the long bar, and I remember that because I can take that long bar, break it in half, and make it into a plus symbol. This circuit only has a single wire that joins the positive end of the battery round to the negative end. Now, most circuits don't just have a wire linking the two ends of the power supply or the battery. They would have what we call a load. So here is a circuit just like we had before, this time with a load attached. Now this is called a resistor. Now it could easily be a lamp or a motor or anything that convert this electrical potential energy into another type of energy, and that is basically the point of an electric circuit. So as we said before, the electrons are repelled from the negative terminal and they are attracted around towards the positive terminal of the power supply or the battery. Now we can define something called the current, which is the amount of charge measured in a unit of coulombs passing a point per unit of time, which is often in seconds. So our symbol for current is this capital I, the charge is Q, and time is measured, given there with T. The units of coulombs per second here can also alternatively be called amps or amperes, which is given the symbol A. Now it's interesting that we don't use the charge on one electron. Actually, 1 coulomb is the same amount of charge as quite a lot of electrons. It's 6.2 something by 10 to the 18 electrons. So when we talk about 1 coulomb per second passing a point, we're actually talking about a truckload of electrons passing a point every second. Now, and I'm really sorry about this, I apologize in advance. It's a strange accident of history that the direction of what we call current, which is the number of charges passing a point per second, but the direction that that is traveling in is actually defined as the opposite direction to electron flow. So I can put in the direction of current flowing that way. Now this is because at the time that current was first defined, they hadn't yet figured out that electrons were the things that were moving. So to this day, we are stuck with this thing called conventional current, and it just happens to be in the opposite direction to the direction that the electrons are flowing. So an electron that is moving, say, from the negative terminal, being attracted around towards the positive terminal, gets to the resistor, it resists its motion, makes it harder for it to go through, and it bashes into stuff. Now, in the process of bashing into stuff, some of its electrical potential energy converts into the kinetic energy, internal energy within the resistor itself. And so the temperature increases. So you've got a situation where you've gone from electrical potential energy to kinetic energy or internal energy. So an electron on the positive side of the power supply has less potential energy. Positive side has less potential energy than the negative side. And an electron passing through that resistor converts some of that electrical potential energy into internal or kinetic energy. And we also find that this power supply acts to bump up the potential energy of the electron. So if we could compare the potential energy on the positive side to the negative side, we would find that this side here has more potential energy than the positive side. Now this leads us to define something called voltage difference or potential difference. Now, voltage difference or potential difference has the symbol V, or sometimes delta V, because it's a difference. It's the difference in potential energy, measured in joules, per unit of charge, which is measured in coulombs, between 2 points. So it's always comparing one point to another, say on either side of a load or on one side or the other of the power supply itself. An equation that goes with that is that the voltage difference is the change in potential energy per unit charge. Units, of course, are joules per coulomb, or we also call these volts, which you may be familiar with. It turns out that voltage difference also gives you an idea of how big the force is that's pushing those charges. It tells you something about the strength of the field which is pushing those charges around. Gets a little bit more complicated than that, but that's a good starting point. I want to introduce or review almost some of those concepts with an analogy. Now you have to remember that analogies can only go so far in representing really what's going on in the circuit. So we might talk about a couple of different analogies. So in this one we have a pump, and the pump is pushing water up to a higher gravitational potential energy, and then the water is flowing down some waterfalls. So the flow of water can be thought of as the number of cups of water passing per second. And if we looked at one of these waterfalls, we might see that there was a change in potential energy per cup of water as it goes over the waterfall. That's a quantity that we could put a number to. So let's, instead of our pump, let's have a battery and some wires and some resistors. And I'm sorry that that's kind of gone over the other picture there, but the charge flow, in the same way that we talked about the water, it's the amount of charge passing per second, and this is called the current. And we can also look at the change in potential energy, so this is electrical potential energy this time, for each unit of charge as it crosses a resistor, or indeed any load or any component in a circuit. So as we go on to analyze what's going on in electric circuits, I cannot underemphasize how important it is that you keep in mind the definition of your current, which is your charge per unit time, and the definition of potential difference or voltage difference, which is the energy per unit charge. It's understanding the definitions of these which will make analyzing circuits so much easier.